So hello, welcome to our lecture 11 of group theory. This is part 3 of group theory, lecture 11. In this lecture, we will just do two more problems and the lecture 11 will end with all its parts. So the problem says that let G under binary operation not be a group and A belongs to G such that then we have to prove that AG is equals to G, where AG is the set defined by A compose G for all G belongs to G. So for doing this problem, we first show that we have to show that we will do this like this. First we show AG is a subset of G, proper subset of G, and G is a proper subset of AG. Then from equation 1 and 2 we will get what? AG equals to G. So for doing that, we will first take an element from AG, say P, and show that this belongs to the set G. So what will happen? AG will become a subset of G. Similarly, we will take an element of G and show this that element also belongs to AG. So G will become a subset of AG, and the proof will be done. So for doing that, we are first taking a element P, say P belongs to AG. So what we can write P is equals to A compose G, because any element in the set AG is of the form A compose G, where and G belongs to the set G, the small g belongs to the set G, for some G belongs to G. AG belongs to G. Since A belongs to G and G belongs to, now this A also belongs to G and G belongs to G. So for and A belongs to G and G belongs to G, and we know what G is a group. First, let me erase these things. Then we'll have some place to write. We have A belongs to G and P belongs to G, and G is a group. So under binary operation, so obviously A compose G equals to P belongs to G. So P belongs to G implying what? P belongs to G implying belongs to G. P belongs to AG implies what? P belongs to G. So therefore AG is obviously a subset of G. Similarly, we are taking an element Q belongs to G. So there Q belongs to G. So there will exist an element X belongs to G such that what? A compose X equals to G. A compose X equals to Q by this set assumptions. So by Q is clearly now Q is equals to from A compose X. So Q will obviously belongs to the set AG. Now from here you can say, now Q belongs to G implies Q belongs to AG. Now, we are starting from where Q belongs to AG and ending where they're implying what Q belongs to AG. So clearly G is a subset of AG. Now from this is equation 1 and this is equation 2. From both we are getting what? AG equals to G. So our proof is done. Next, we have said that G under binary operation not is a group and A be an arbitrary element of group. Define a mapping. So I think this is written rho alpha from G to G, G set to G, rho alpha, such that rho alpha x equals to x compose A where x belongs to G. Prove that this mapping is a bijection. First we have given this G under binary operation is a group, and this mapping is like this: rho alpha is equals to rho A, basically rho A is equals to x compose A for x belongs to G. Now let's to show this mapping is bijection, we have to prove that this mapping is both surjective and injective. To do that, first we have to trying to prove this that this mapping is injective. So taking two elements x and y belongs to G. So now rho x will be what? X compose A, and rho A y is equals to y is y compose A. Now if we considering this, that the rho A is equals to rho x equals to rho y implies what? X rho x x compose A equals to x compose y compose A. Now by right composition cancellation law, we are cancelling the right element A and getting what? X equals to y. So rho x equals to rho a y implying what? X equals to y. Therefore what we can say, if x not equals to y, rho x, the mapping, the image of x under the mapping is not equals to under the mapping image of y. So we can say that this mapping is injective. Similarly, rho be an arbitrary element of the codomain set G, G say I am taking some any arbitrary element from the codimension G, and A belongs to G. We already know that A belongs to G. So there must exist a unique element Y in G. From the previous problems, we can say that there will exist a unique element such that Y compose A equals to P. So for each so Y is a pre-image for, so, and since P is arbitrary, for every arbitrary element we are finding an element such that Y compose A equals to P. So this is proving what, uh, row for each element P we are having an element Y such that row A Y equals to P. So every element in the codomain has a pre-image, so we can say what, row, the mapping row is surjective, so the mapping is both surjective and injective, so the mapping will become bijective mapping, or row is a bijection. So our proof is done, and here we are ending the lecture 11 part 3, and the total lecture content of lecture 11 is done. Thanks for watching. Please like, share and subscribe. Bye bye.